In this lecture, let's discuss about Cortex-M processor core registers. Okay. So again, I'm going to refer to the generic user guide of the Cortex-M4 devices. Okay, and the discussion will be similar if you have Cortex-M3, M0 processor-based microcontroller. Okay, so the discussion will always hold good. Now, in this document, I just opened this section, core registers, and here you can see that these are the processor core registers. Okay, and these core registers are actually residing under this Cortex-M4 core, okay, or Cortex-M processor core. Okay, so here you can see that the registers from R0 to R12, okay, are general purpose registers. Okay, so that means, so I'll just write that, okay, R0 to R12 registers, okay, are for general purpose. Okay, so that means these registers are not to R12. You can use it for general purpose, like for data operation, data manipulation, to store data, okay, to store addresses, etc. And all the registers, all the core registers are 32-bit wide. Great, so now let's move forward. The register R13 is called as stack pointer. Okay, so I'll just write that. The register R13 is called as SP, that stands for stack pointer. So that means this register is actually used to track the stack memory. Okay, so I will talk about stack memory and the stack pointers in detail, okay, in the subsequent lectures. Okay, but for the time being, just know that, okay, R13 is a stack pointer which is used to track the stack memory. And beside this R13 register, two more registers are mentioned. That is PSP, which stands for processor stack pointer, and MSP, which stands for main stack pointer. And these registers are called as banked version of stack pointer. Okay, so more on this I will cover later. So all these three are actually stack pointers. Okay, but one among these will be active depending upon the mode of the processor, which I will talk later. Okay, so don't worry about that. So now let's move forward. Now the register R14 is called as the LR. LR stands for link register. Okay, so now what we'll do is we will go to the description of the LR and we'll read about that. Okay, so I'll just go to this link here, okay, and it takes me to the description of the link register. Okay, just read this sentence. The link register is register R14. It stores the written information for subroutines, function calls, and exceptions. Okay, on reset, the processor sets the LR value to this value. Okay, so now let's not give much stress upon this sentence, but this sentence is very important, that the register R14 stores the written information, okay, for subroutine, okay, or function call or exception. Let me explain the use of link register, that is LR. Let's take the case of function 1 and function 2. Function 1 calls function 2 in this case, and the function 1 is called as caller and function 2 is called as callee. Here, this is a place where function 1 calls function 2. In terms of assembly language, it is a jump to another address. That's why PC is loaded with address of function 2. That's how execution goes to the function 2. At the same time, what happens is the LR is loaded with the address of the next instruction. That's how processor maintains the return address. PC is loaded with new address, LR is loaded with the return address. and when the function 2 finishes here, it has to return to function 1. At that time, the saved LR is copied into PC. That's how PC jumps back to resume function 1. That's the use case of LR. So that's why LR is used during function call or subroutine call to link back to the caller. Let's see this with an example. Here I have a code, and this is our older code. Here you can see that this is a main function, and main function calls this function generate interrupt. And now let's analyze this with disassembly. Here is a place where the main code jumps to this function generate interrupt, BL. BL stands for branch with link. When you use branch with link, the link register gets updated with a return address. So what's the return address here? So this is a return address, isn't it? So this is the address of the next instruction. So whenever this generate interrupt function returns, the execution must continue from here. So that's why this value will get updated in LR. Okay, so now what's the value of LR? The current value of LR is something different. You can see here. Okay, and now let me activate this instruction stepping mode. Now let me do single step. So when I do single step, the control will go to generate interrupt. You can see that. Okay, but the LR is updated with the link address. To this address, the processor must return when it finishes the generate interrupt function. Okay, now let's see that. So now let's see where generate interrupt ends. So here it is. So this is a place where the generate interrupt function returns to the caller. Now look at the instruction. Instruction used is BXLR. BX stands for branch indirect. When processor executes this instruction, the value of LR is copied into PC. So that's how the execution control resumes back to the caller. You can see that. Let me keep a breakpoint here and let's run. So now you can see that the code stopped here. Now when I hit single step, this LR value is copied into PC. You can see that. Okay, so LR value is 22B and PC is this much. Now let me do single step. You can see that value is copied into PC. Now, but you can see that here the value 22A is actually maintained as 22B. So that has got something to do with T bit of the XPSR register. Okay, so that's the use of LR. LR links back to the caller during function call or subroutine call. And with that note, I would like to end this lecture. Let me know if you have any questions. I will see you in the next lecture.